So thank you very much, first of all, to the organizers for putting this together and the invitation to give a talk here. I'm going to try to reduce the distance between the Swampland and the Bootstrap, or at least aim to, or motivate you to try to think about it with me. Collaboration is very important. As Simon just pointed out, I'm not an expert on causality as these things because I put the date wrong. But I hope that with your input, we can make it work. So, yeah, so I have prepared this talk especially for this workshop and this audience, okay? I'm gonna choose some Swampland constraints. I cannot talk about everything, something specific that I really like. Make a bit of a review, focusing on some recent developments, some exciting things, and putting many open questions, okay? So I want to drive discussion, if not now, later on, whenever you want. So there will be many open questions, especially in those points in which I think would be interested for holography, Bootstrap, and so on. Okay, so I think Swampland and Bootstrap share the same goal, even if we use sometimes different techniques, different approaches. In the end, we are just trying to understand what is the space of consistent UV-completed theories. In the Swampland in particular, we are interested in those theories that are coupled to gravity. Okay, so we want to understand what effective field theories with coupled to gravity can be UV-completed. And if they cannot, we say they belong to the Swampland, but it's just terminology. So there are many points in which there is a clear connection, and I think it would be very useful to benefit from each other. Okay, we can use both intuition from Swampland, techniques from Bootstrap, and vice versa. And there are many things that I could be talking about. These are like the main Swampland ideas, in which in each of them we can try to think whether we could address it or prove it using Bootstrap. As I said, I'm not going to talk about everything. I'm going to stay here in the program, so I'm very happy to discuss. We will probably also lead a discussion about these things. So today, I'm going to focus on those questions that are related to the distance conjecture, which is one of the central ideas of the Swampland, and that still is not super connected to Bootstrap and holography, so it would be nice to explore it further. Okay, so let me also mention that from now on, there is no counterexample to anything I will say, not even potential proposed counterexample, but there is no general proof either, okay? So in general, all the support comes from string theory data for this particular Swampland constraint that I'm going to talk about. Sometimes we have some arguments coming from black holes, but they are not very complete. So that's why it would be very nice to understand better if this particular Swampland constraint is a general feature of quantum gravity, and in order to do that, we need to address it from different approaches, no? And that's why it would be very nice if we can derive it from general principles. Okay, so what's the distance conjecture? Well, I guess probably many of you have heard about it, but let me just quickly say, just in case. So the point is, as I said, it's an observation that first came from string theory. So in string theory, you don't have free parameters, like all these parameters, couplings, masses are parameterized by vacuum expectation value of some scalar fields. So you can probe different theories by moving on the field space, on the modular space of string theory, in which we can equip with some metric, which is given by the field metric of these scalar fields. And the statement is that when you move in this modular space, if you move parametrically far away, if you approach an infinite distance boundary of the modular space, you should get an infinite tower of states that become exponentially light in terms of the geodesic distance that you travel in the modular space. Okay, so from an IR perspective, what this means is that the effective field is going to break down. You cannot make it valid for a parametrically large field variation, so it puts a bound on the quantum gravity cutoff given by the mass of the tower of the states. While from a UV perspective, what puts is like constraints on the field spectra and how the field spectrum transforms, no, as you move in the modular space. It's very deep it's very intrinsic of string theory because it's linked to all the dualities that we know and love. Like whenever you go to infinite distance, like some volume becomes large or small, or some string coupling becomes small or large. You get a new description, you get new towers that can be related to each other by dualities, and so on. So understanding the possible natures of the tower, the possible towers that you can have, is like understanding what are the possible dualities that get manifest, and what are the possible quantum gravity resolutions. Okay, so in the end you get a tower, but something is going to happen. Maybe you open an extra dimension, or you go to string theory. And if we could, from bottom up, understand what are the possibilities, it's like predicting that in quantum gravity you need to have either extra dimensions, or you need to have string modes, and so on. Okay, so we can think of having like a map, no? How to connect even different modular spaces by these infinite distance limits, and where in the end everything will be connected or not. Okay, so one of the things, I mean, when studying this in string theory, I mean, there has been plethora of quantitative tests. One of the goals was to study these infinite distance limits in lower dimensional compactifications, because you don't know what's going to happen. Like sometimes maybe you go to some infinite distance limit and maybe you discover a new, I mean, like the best thing would be to discover even a new string theory, no? Or new resolutions that you didn't know about. Like sometimes when you compactify, you can connect different components of the modular space in the same modular space in lower dimensions. So it's interesting to understand what are the possibilities, no? And in principle, something new could happen, I don't know. At this moment, I must say that so far, all we have found are string theory examples, so I will describe. So let me give you the outline and then explain this in more detail. So what I'm going to do is to tell you what are the types of infinite distance limits that have been found in flat space, what we know about them, and what we expect to happen. Then I will go to ADS, okay, and see how these things apply in ADS, and what are the possible connections and interesting aspects that would be nice to prove. And then I will tell you a bit about the mathematical structures that we have uncovered by studying these towers and these modular spaces that could also be useful maybe for the CFT. And then at the end, I will tell you some ideas about how to go beyond the modular space. Okay, so the modular space are the massless fields, and then you can have a potential and what's going on. I mean, how the story is modified. Okay, and how we can maybe try to define a distance between theories more generally, even if they are not connected by the modular space. Okay, so let me start with this type of limits. I was saying there are different limits that could arise at infinite distance. So far, from string theory, like all the computations have been done, it seems that at every infinite distance limit, you can always find some frame in which the limit corresponds to either string perturbative limit or a decompactification limit. Okay, so that's why I was saying that on one hand you would expect that maybe new things appear, but so far all the corners are either one of the two types. And these are the two towers that we typically get. So on one hand you get higher spin string modes, on the other hand you get Kaluza-Klein towers, right? Now the structure, well, this is just kind of a review. I mean, you just have some tower with different degeneracy of the states in one or another case. Here I'm just putting the typical expression for some unwarped compactification. I mean, in general, as Alessandro explained us yesterday, Kaluza-Klein spectrum can be a bit complicated. So that's also something that is important here when studying these conjectures. And we have, I mean, this is the mass of the states of the tower. But then, as I said, if you have an infinite tower of states, Einstein gravity is going to break down. You cannot have infinitely many weakly coupled fields. So at some point, quantum gravity comes into place. You cannot have a quantum field theory anymore in the same number of dimensions. And the quantum gravity scale, we parameterize it in terms of this species scale, okay, at which quantum gravitational effects become important. So in the case of the string tower, it's of the barely of the same order than the mass of the first state of the tower, so the string scale. There's some logarithmic correction, but it's more or less the same order. But in the case of the Kaluza-Klein tower, if you just compute the species scales for a Kaluza-Klein, you get that is of course, the higher dimensional Planck mass, which means that is above the Kaluza-Klein scale, right? The first state of the tower. So here you still get some states, and then you get the quantum gravity scale. So I'm reviewing this because sometimes when we work from Bootstrap, like how we give an interpretation to the cutoff and the gap, I find that sometimes we always use kind of this large gap, like this separation with higher spin fields. But I don't know, like I'm always curious to understand better how to distinguish the two scenarios from a Bootstrap approach.
Sorry, the lambda actually is the scale above which you cannot ignore loop effects?
Yes, that's one of the, so there are several ways to think about it. One is that indeed, like the loop effects become of the same order than the tree level. So you don't have a QFT will couple to gravity anymore. It's also
a string scale times log of G, log of the string couple.
Yes.
That's a lower scale than I would have. Why do loop effects come in so soon?
So soon?
I would have thought it would be some MS times some.
Well, there's a difference between these two, which is that here you still have a, so it all depends what is the frame you're considering. Like if you're fixing the Planck scale or the string scale. So when we work on the worksheet, like we are thinking of the string frame. So the point is that here, so let me say, so the difference between these two is that here you can still have a weakly coupled theory to gravity. The point is that has higher spin fields, okay? So when I say the loop, I mean, typically better thought here, that here really becomes strongly coupled, like gravity becomes strongly coupled, okay?
What I'm asking is probably very stupid, forgive me, but say a perturbative correction is suppressed by some power of J string. And then there's a function of energy. I would have expected that you need to go to some inverse power of J string before loop effects became very important. Why is it a log?
Inverse power of G string. So I mean, if G string goes to 0, the point is that this cutoff goes to 0, right?
This is the cutoff about Netflix's field theory description, like string perturbation theory still works.
Exactly. So the QFT, the effective field theory description breaks down, then you have string theory weakly coupled to gravity, and that's fine.
Weakly coupled string theory still works.
Yeah. That's what I said. So the resolution here is that you get higher spin fields, so it's not a QFT anymore.
Okay, fine.
Yeah, that's fine. Ask whenever you have a question, please ask. Yes. Okay. And then the point is that if you just have these limits, also the exponential rate of the tower, which in principle is always said that it's like a free parameter in the distance conjecture, is some ambiguity, order one factor, you don't know what's going on. It's also determined in a sense, like depending what is the nature of the tower, you will have a different rate at which the tower becomes light. And if we have just a critical string in flat space, this is the rate. If we have a Kaluza-Klein tower and a warp, like a toroidal compactification, this is the rate. It depends on the dimension of the space-time. And here also how many dimensions you decompactify. So if you get information about the first state of the tower, you can also get information about what's going on in the quantum gravity resolution. Okay, so as I said, so far these are the only two limits that have been found, like studying type 2, Calabi-Yau compactification, different limits, and so on. There's always some frame in which is one of the two. And then these people propose that this is a general thing of quantum gravity, but as I said, it's only based on the string theory. It would be nice to understand if this is necessary. It's like trying to understand whether, right, like quantum gravity resolution will involve necessarily higher spin fields or not. Now, if you also take that these are the only two possibilities, you could also aim to give a lower bound for the exponential rate, which is interesting for phenomenology, because if you give a lower bound on the rate, you are giving an upper bound on the field range. So you can use it to constrain in a more precise way models of inflation and so on. Okay, so these people, based on this and string theory examples, propose this bound for the exponential rate, which is just as you can see here, is the value for the critical string, because Kaluza-Klein towers have a larger value of alpha, so this is always larger than this. So you could say that this is the bound and it's saturated when you have a string perturbative limit. Okay. Okay, so this is for each limit independently, but it's very interesting when I was saying that the distance conjecture is linked to dualities. That's more about global information, about how some limits compared to other ones, no? About global information of the moduli space. So it's nice to think how to talk about the distance conjecture when we have many directions and we want to think more globally about it. And this is why we formulated this convex Hall distance conjecture. And the way it works is that, well, you can define what are called these scalar, it should be scalar charge to mass ratio, which is like the exponential rate when we have this exponential behavior of the mass. This is the Bilbine of the field space. It's called the scalar charge to mass ratio because, in fact, if you have some massless scalar, they induce some force and Yukawa force in your theory, and the charge under this force is the derivative of the mass. Okay, so it's like it's kind of the same ratios that you use for the weak gravity conjecture, but for comparing scalar forces and gravity. So the exponential rate of the tower, which is really like one of the big questions of this conjecture that are useful for phenomenology, is just the projection of this scalar charge to mass ratio and the corresponding geodesic trajectory. So, as we pointed out, roughly speaking, it seems that the distance conjecture with a lower bound on the exponential rate is equivalent to require a sort of scalar weak gravity conjecture, because this is like a charge over the mass and has to be bigger than some value. And I put here almost because this is actually stronger, because this is a local statement that has to be satisfied at every point in the modular space, where this is more like an asymptotic behavior that you have to combine different limits. Okay, so instead of at each point, but it has kind of the same shape, and therefore we can use something that is very useful for the weak gravity conjecture, which are these convex halls. So when you have several fields, what you have to require is that the bound is satisfied for every direction, and this is going to happen if the convex halls, if I have different towers of states, I can plot where they are, what is the scalar charge to mass ratio, and if the convex hall of all these vectors contain some ball of radius alpha 0, then I can guarantee that if I move in some direction, some arbitrary direction, the distance conjecture will be satisfied with some exponential rate that will be bigger, that will be at least alpha 0. Okay. And this is because the larger, right, the exponential rate, the fastest the tower decays. So the convex hall is like it's taking into account the leading towers. Okay, everything that is heavier will be inside. So this is nice because if you now combine it with a specific value of this alpha 0, this is a quantitative thing that you can aim to check and use to obtain more global information about your modular spaces. So this is something that well, Heidenreich, Frudelius, and Muldrow Etheredge, and others started to do in this paper. And I'm just gonna give you one example and then move to other things. But I'm starting to love this type of diagram, so I just wanted to tell you a little bit about it. So this is 10-dimensional day to be on a circle. Okay, so it's a simple example. We have two moduli. We have the radius of the circle. We have the dilaton, right? The string coupling. This would be the 10D dilaton. I2B is dual, so there is like an S duality. I have, sorry, let me put everything. So we can plot, these are the scalar charge to mass ratio. So it's like the exponential rate for each tower, okay? And we have different towers that become light depending where we move in this modular space. So we have different descriptions, right? We can have at large radius, small coupling, we have type 2B on the circle, then we get a T-dual description when the radius becomes small, which is type 2A, when we become strongly coupled, we get M theory on a torus. And at each of these interfaces, right, we get some tower of state that becomes light, either the Kaluza-Klein modes, the string modes of the fundamental string, the winding modes that are T-dual to the KK modes, and this dual version. And this is the sphere, this is the ball of radius 1 over square root of 7, which is precisely this bound on the exponential rate, that indeed it's associated when you get stream modes, and is satisfied for the Kaluza-Klein towers. And you can study, I mean, here the distance conjecture is of course satisfied, but you can start to extract interesting consequences of this global picture, because for instance, if you have a string perturbative limit, you need to have also some decompactification, because if I only have string perturbative limits, I'm going to cut this ball. Okay, so you can try to think what if one limit is of one type, maybe what the others can be, and vice versa. So it gives you information about the dualities and so on. And then it opens the question. There's something that I'm thinking about with Jake and others, whether we can try to bootstrap somehow what are the possible diagrams that one can have, okay? Which is like understanding what are the types of limits. This is 1 over square root of d minus 2. D is the dimension of the spacetime, which is 9 here, so 9 minus 2, 7. So it's the lower bound that you would expect. Okay. So this was the situation in flat space. We can, of course, you can consider many more modular spaces and so on. Let me tell you a bit about ADS now. Okay. How am I going in time? No. Okay, I should rush a bit. It's fine. Okay, so in ADCFT, so you can try to ask the same question. The modular space now is a conformal manifold. And it's interesting that this conjecture seems to hold quite generally, like even beyond weakly coupled ADS. So even if you have weakly coupled ADS duals, it seems that whenever you go to infinite distance in the conformal manifold, measured by the Samologikov metric, you get towers of operators that saturate the unitarity bound. So it would be, if you have a holographic dual description, it would be equivalent to having massless towers of states. And it's a bit different depending on the dimension. So in 2 dimensions, it was conjectured that the only way to go to infinite distance is to have the scalar gap going to 0. In higher dimensions, we propose that the only way to go to infinite distance is to have the higher spin gap going to 0. Because all known examples so far of infinite distance points are free points, and therefore they have a higher spin current. And then one can show, because this is just the perturbative limit, the Jamil's coupling go to 0, that the anomalous dimension of these currents behaves exponentially in terms of the Samologikov distance. Okay, so it's consistent with the distance conjecture. But it would be nice to understand if this is indeed the only possibility, or also try to classify, right? Like what are the possibilities, and so on. And as I said, like here in higher dimensions, there are no pure decompactification, which maybe is also related to all these questions about the scale separation and so on. And all limits seems to be associated to tensionless strings. The exponential rate can also be computed very carefully. It's just using perturbative field theory. And it tells you information about what is the portion of the theory that is getting free. Okay, so it's the central charge over the dimension of the X group. You can bound it because the dimension of the X group cannot be larger than the central charge. This is when you have a holographic dual, so you write the distance in Planck units. Okay? And then it's something interesting I wanted to let you know is that we were checking, we were computing this for examples to see what are the numbers that we get. And if you take the full classification of 4D superconformal field theories that admit a large n limit and have a simple gauge group, we only find 3 values. So it's, I mean, and this is because all these theories have only 3 values of the A over C. So I was also wanted also to pose the question in case people are familiar with this. I didn't know this, but I don't know, in case someone already noted, and there is some feature that characterizes the 3 different groups of theories. Because in flat space, it was very useful to understand the different rates, because that's the different natures of the tower, the different limits, and it tells you different quantum gravity resolutions. So I'm wondering if this can somehow hint that there are like 3 types of tensionless strings or worships, or I don't know why they lie on these three types. At least in flat space, it really gives you information about what is the nature of the tower. Something also, well, of course, they satisfy the bound I was talking before, but it's different because, I mean, you would expect that they are all tensionless strings, so they should saturate it. They do not saturate it because the quantization of the string in ADS is different. We have a highly curved ADS space, so you have to be more careful, but okay, it still satisfies. And there's a funny coincidence also that these three numbers also happen to be, maybe it's just a numerical coincidence, but happen to be the exponential rate that you would get for a Kaluza-Klein tower if you were decompactifying to 11, 9, or 8 dimensions. So it was very funny because this is a complicated formula, so you are not supposed to get an integer necessarily, but somehow you get an integer. Maybe just a coincidence, although yesterday I learned from Nikolai that actually the super QCD examples that have this exponential rate, there was a paper by Leonardo saying that maybe there is a way to understand that there are only 8 geometric dimensions. So I don't know if that means that we can really think of this somehow, but I don't know, something to explore. And just a last comment about ADS, and I move to the last part of the talk. You can also try to do the same game with this convex hull and so on, like to consider more globally the different limits. This is just n equals 4 super mills. Hope you all know about it. And the point is that, of course, when you want global information, I mean, you don't have the same description everywhere, no, the same than before. So it's if you think only on large radius, I mean, we are in the supergravity regime, okay? So these are like the two lampposts that Rajesh was talking about. I will have the top coupling going to infinity or to 0, the radius going to infinity, or GS going to 0. Here, I mean, you get the Keki modes, you get the stream modes. This is where the stream modes would be, saturating this according to supergravity. But if you only have, I mean, before in type 2b, the point is that this was satisfied because we had the winding modes, but here we don't have these winding modes. So if this was everything, this would be violated. But of course, what happens is that as you move to this regime, this supergravity formula is not valid anymore, like the string modes, and you have to quantize the string on a highly curved ADS. It's better to think of the CFT dual description, and according to the CFT, the anomalous dimension behaves this way, so that if you extrapolate to what would this correspond for the mass of the stream modes, you can compute that they should be here, which is precisely like continuing this line, perfect straight line, so that you satisfy this convex Hall distance conjecture. So CFT is saving the story as usual. Okay, and then you get this value. So in the last 3 minutes, I want to tell you just 2 things that will be hopefully quick, or I will try to make them quick. One is about some mathematical structure, so we'll just put some open question, and then if I have time, otherwise I will just skip it, how to think the distance between theories. So I just wanted to say that when we were checking this conjecture in Calabi-Yau compactifications, we uncover and we use a lot this machinery of asymptotic Hodge theory, Misch-Hodge structures, because it gives you the, I mean, in 4n equals 2, this is a scalar-Kähler manifold, so you can compute both the BPS masses, the metric in terms of some periods of some holomorphic form. And these theorems tell you what is the behavior, the asymptotic behavior of these periods as you go to the infinite distance limit universally in terms of the behavior of the monodromy matrices. No? So as you go around the singularity, the periods undergo a monodromy transformation, which is some descriptive symmetry from the EFT perspective. And you can encode the information of the periods and therefore the metric and everything in terms of these monodromies. And therefore, we could show that infinite distance was correlated to having a monodromy of infinite order and therefore an infinite tower of BPS states. Now, this is something that is always in my to-do list to understand better if we can apply this to 4n equals 2 CFTs. Okay, so this is something we know in 4n equals 2 supergravities, even if they are non-compact, and was very useful to classify all possible limits, and would be very nice if something like this can also be shown to apply for the CFTs to understand better the conformal manifold. And maybe try to show if all points are free points, because that's encoded on the symmetry group and so on. Okay, so this was one point. Quickly, the other point is that there is something that happens also when you use these theorems, and is that when you go to the infinite distance, you always get some sort of hyperbolic metric. It's like an ADS2. And then these theorems of Mischel structures are actually telling you, I mean, this is just like it's not necessarily a duality, so far it's just a mathematical map, but they just tell you how to reconstruct like the geometry, like the bulk information from some data that is at the boundary, at the infinite distance boundary, that actually exhibits some SL2C algebra, which are these monodromies. Okay, so all these theorems are precisely telling you like how you have this algebra and how you can split the cohomology group into subspaces that are eigenstates of these monodromies, and how to obtain the information about the radial coordinate as you approach the singularity when you remove the infinities from this boundary data. So this is what Thomas Grimm and Cecotti like to call like moduli space holography, see if one can try to make sense of this. Doing holography in the moduli space, and they propose even a bulk action that would reproduce the geometry. Okay, so this is also some interesting point to think, and if I have a couple of minutes, then let me tell you a few words about how to think of the distance between theories. So far everything I said is about the moduli space. You have massless spheres, very easy and nice and clean how to define distances. In terms of the field metric or by Peterson metric. But physically then, once we break supersymmetry, we're going to have potential, we're going to leave some directions, others will get, some running, and it would be nice to think more generally, you know, how to think about this. So, for instance, I can have some runaway behavior, or I can have discrete vacua, and what seems to happen from string theory is that still, the distance conjecture works in the sense that you still get an infinite number of states, even if you have a scalar potential, that becomes massless at the infinite distance limit. And as long as, of course, the potential is not obstructing the infinite distance limit, okay? So below a certain cutoff, you can still describe an EFT which has an infinite distance limit in this field space. But it's still not obvious how to properly define the distance, no? How to show the exponential behavior of the tower. So there are some proposals, like for instance, when you have this discrete set of ADS vacua, Kungrun and collaborators propose, sorry, this should be here. So this is the ADS distance conjecture. So propose that if you think of the space of metric configurations instead of scalar fields, you can define this distance. That would imply that indeed, since it should behave exponentially on the distance, in the end, the mass behaves as the potential to some power, which is what happens in all these ADS examples. And you can see here the importance of this exponential rates I'm talking about, because this exponential rate is what is going to tell us if we have scale separation or not. So it's not about satisfying the distance conjecture or not, it's about all these numerical factors. So try to classify what are the possible limits and what are the values that we get. And for runaways, it also happens that both the mass and the potential decay exponentially. So they also, like in all examples, there is always this sort of relation between the mass and the potential. That would be nice to derive more generally if we have a proper notion of distance. Okay. So last slide. So the goal was some ongoing project I have with Kungrun and Miguel, is that we are trying to define a distance between different EFTs more generally. This is an old question, very interesting for many communities and different reasons. Morally, the first thing I think that comes to your mind is that you can use as a distance the action of the configuration, right, that interpolates between the two theories. Okay, so this is the Euclidean action, and it has a nice interpretation in classical mechanics because it's actually the mapper to this action, so one can show that it's indeed a well-defined metric and it's positive definite and can define a distance. And morally, it's like the tension of the domain wall that interpolates between the theories. Okay. So we are thinking about it. it's nice that actually this is a notion of distance which is energy dependent. So it depends what is the energy at which you probe the theory. But we can show that when the energy becomes very large, so from the UV perspective, everything seems massless. And actually, you can show that this recovers the modular space distance. But if the energy is very small in comparison to the potential barrier, you recover actually this ADS distance that they propose in terms of the log of the potential. So giving a motivation for the relation between the mass of the tower and the potential. Okay, so that's it. So if we have this distance, it's like, as I said, the tension of the domain wall. So according to the covariance conjecture of Jeck and Kumrun, which is just quickly, is required to avoid topological global symmetries, it says that you should always have a domain wall interpolating between any two theories of the same dimension, which would mean that this distance that we are talking about should always be finite from the UV perspective. So it's like the infinite distance, something that emerges in the IR, which connects with some ideas of the emergence proposal that you can ask me about, and give a sort of notion of finiteness of the landscape in the sense that everything gets connected from the UV. So this is it. Thank you for your attention. And just so you know, we have always this online series of Swampland seminars on Monday. Everybody's invited. If you are interested, just send me an email to me or Miguel. Thank you.
Thanks for the talk.
Questions?
Near the end, you mentioned the Euclidean trajectory. So it reminded me that in Euclidean theories, the metric on moduli space is in fact non-Euclidean, typically. So what would that mean for the formulation of the distance conjecture?
What do you have in mind? Is the metric?
Like you take a typical Euclidean supergravity, the moduli space metric is of indefinite signature. Roughly speaking, because of axions, get a flip in the kinetic term.
Yeah, but this is, so when you study the geodesics, that's not going to matter, right?
No, it is. I can have null geodesics. So, or I can even geodesics which are time-like. I don't know a formulation of the distance conjecture in that case.
I don't know. I should think. I mean, the thing I have in mind is just that. I mean, in the end, it should be the same. Like, it should be the geodesic distances, no, in terms of this metric. What matters for this generalized distance conjecture? In those cases, when you recover the field space, I mean, you can show that if the energy becomes small, you really recover just the field space metric. So I'm not sure where the concern you have will appear in this. Like, because like you have the square root of E plus V times the metric, and if the
concern is that distance can be positive, negative, or zero for curves.
No, but here has been shown that the Mappertuis action is positive.
Okay, definite. But I mean that in general, not say for a domain wall trajectory, but just in general.
Maybe that's okay. So yeah, maybe that's the point. So in general, maybe you can have other types indeed that's not well defined. But here, this is a function, so you should find the path that minimizes, no, this function that extremizes. And for that, I mean, it's fine. It's a minimum, and it's always positive definite. That is, it's called the Jacobi metric. So maybe the point is that the problem does not appear in that case. Yeah.
Any other?
I just wanted to ask about this attempt to define distances between effective field series. I guess in the case of CFT2, there was an attempt to define distances using a conformal interface. Mm-hmm. What you are trying to do seems very similar to that, but in those cases, I think the conclusion was that the tension of the interface didn't quite define the distance because it didn't satisfy some basic properties like a triangle inequality.
Yeah, I need to. So I'm aware of this. I need to revisit it because I'm not sure where the problem is exactly, how what's going on. Because as I said, like here with this Mappertuis action, it's always positive definite, and it satisfies this triangular inequality because it's always a minimum. But I have not thought yet about the dual of this and how this would translate to. It should be related to the conformal interface, but I have not pointed out where, how the problem is solved or what's different exactly. So I don't know. It's something to think about. It's still ongoing. So.
Hi. So you compared the definite value for the lower bound for the exponential rate to the order 1 number in the, say, weak gravity conjecture, and that's fixed by the charge to mass ratio of an extremal black hole. So can you think of this 1 over root d minus 2 as some extremal object, the charge to mass ratio for some extremal object?
Yeah, I've tried. Exactly, that would be nice. So the difference between the weak gravity and the distance that for the weak gravity you have arguments based on black holes and this order 1 factor related to extremality, so you can compute it from bottom up. The distance, that's what we are missing, right? So this suggests that maybe, I was thinking, okay, maybe with this scalar charge to mass ratio, you can try to give a bottom-up origin. But the problem is that if you just think of a balance of forces, it's a different factor. It's not 1 over square root of d minus 2. So it doesn't have this interpretation, this lower bound that Heidenreich and the others proposed. So far, there's no physical motivation for this 1 over square root of d minus 2 beyond string theory. But yeah, indeed, I mean, that would be one of the goals, try to have a bottom-up explanation of what is, how fast the tower should decay, no? What is the extremal region.
Any other questions? Nothing on Zoom?
Can you say a little bit more when you're talking about infinite distance and ADS, about 3 types of tensionless strings? What's the difference? From the CFT point of view? Or?
Yeah. So these are, I mean, how we derive it is just that, I mean, you can compute how the anomalous dimension behaves. Depends on the dimension of the gauge group that gets free, because that's what appears on the factor of the Samolov-Ikov metric. And then that's when we write the distance in Planck units, thinking that there is some large n, so like some dual, some dual version. Then the exponential rate becomes the central charge over the dimension of the gauge group. And you can just compute it. And it happens that for these cases with simple gauge groups, there are only these 3 values that are correlated to having only 3 possible values of A over C. Why there are only these 3 values? I don't know. I don't know what is the feature. I mean, of course, it's about the field content, but I don't know if there is any other feature of the CFT that can tell you what groups you should be or why one or the other one. And it's true that it maps to the rate of the tensionless string, like how the string is becoming tensionless. So there are 3 ways, like 3 rates at which the string becomes tensionless. One associated to the critical string, and the other 2 are non-holographic, so they are like, it's large M, but there's no large cap, so they are like non-critical strings somehow. And it seems that there are 2 different rates at which this can happen, so it would point out that maybe there are 2 types of the spectrum for the non-critical strings, but I don't have I don't know.
So the idea would be that if I set it as a bootstrap problem for the CFTs, approaching this high-spin point, there should be discrete families of solutions.
Yeah, for instance.
Right. Let's thank Irene again for a great talk.